Hello everyone, welcome to the extra session for the course on control systems. So all of this time before for the 12 weeks, we went through most of the theoretical concepts. We went through some MATLAB problems as well, but yeah, today we'll have a full-fledged session on MATLAB where we might solve some questions today. And we might also have some more insights into how are the questions dealt with in MATLAB. Like you use a long, lengthy process to solve Bode plot or Nyquist stability criteria or a root locus, but MATLAB commands are really handy. You can directly have a simple function. You can call a simple function and you'll get the plots there itself. You also make approximation for many performance specifications, but MATLAB has complete set to find the exact solution corresponding to all of those performance specifications as well. So validating your answers or getting them done in a very short amount of time is really helpful when it comes to MATLAB. Okay, so we'll have a very few questions to which we are going to discuss today, and I'll provide you with some resources that will help you in practicing the MATLAB questions even more. And this PPT is definitely going to be shared with you. You can always refer to it back and forth. Moreover, we had a few questions that we already did in our MATLAB session, right? So questions related to Bode plot, Nyquist plot, and then some very basic questions in which we can just find the transfer function by defining the coefficients of the numerator and the denominator were there. There are other ways in which we can go from state space to a transfer function to state space representation and vice versa. So all of these things are possible. Okay, now we'll start. Okay, the first question that we're supposed to solve in MATLAB is the following. You're given a forward and feedback transfer function, and we want to determine the closed loop transfer function with the step response. If this is the thing that you're supposed to do, what will you do? So before this, I'll write something to have a clarity, and then we'll proceed. So this is the forward path transfer function. This is the feedback path. Now, your closed loop transfer function is given as G1s upon 1 plus G1s G2s. You can substitute here and you'll get GS to be equal to 10 upon S plus 10 upon 1 plus 10 upon S plus 10 into 5 upon S plus 5. When you try to simplify this expression, you'll get it equal to be 10 into S plus 5 upon S square plus 15S plus 100. Okay. Now what we want to do is, you have got GS is equal to 10 into S plus 5 into S square plus 15S plus 100. Let's try to find out the step response for the system, and also what is represent it in the form of closed loop transfer function. Okay, so how we'll do this, I'll show you. Okay, so this is MATLAB. I have referred many times to this window till now, and yeah, it is very simple. This is the basic editor part in which you are so this is the time when my sorry, did I miss something? Okay, so this is the time when we are defining the MATLAB function, MATLAB program in this format. So earlier, whatever we did was in .m file. where you would use new and you would have script. From there you can write everything in editor and run it in the run it, and you can get the output in the command window. Whereas this time we are using something which is in MLX format. So this is a live script. Like Python, it helps you write the code and get the outputs in line. So this .mlx editor helps you in doing live coding, live interaction. So this is really a helpful tool. Okay. Now, for the question that I showed you, so this was your question where you are given a forward and feedback transfer function. We want to find out what is the closed loop transfer function of the system and plot the step response. So it is very simple. So if you see from here, your your coefficients, what are your coefficients? That is really important. 10 is already a gain. For s it is 1. For s to the power 0 it is 5. For s square it is 1. For s it is 15. For s to the power 0 it's 100. Right? So it's the same thing. We have just written the coefficients over here. Num is the variable that stores the um, numerator coefficients in the form of an array. Denominator also stores the coefficients of the denominator terms in form of an array. Now we create a transfer function. TF is an inbuilt function that can be called to make transfer function out of numerator and denominator. Okay. Once you have the transfer function ready, you can simply call, so figure is used to uh, make a point that yes, I want to generate a figure right now. Step 2, G. G is my closed loop transfer function. If you call the function step on G, it is going to plot step response for you. Title is for the picture and grid is on. Okay, I'll run this section now. So, okay, this is coming here. So this run section helps you in running this part, and then you can see the output. So I've run this section. I'll bring it in inline format. I think this is taking some time. Hold on. Yeah, this is the step response. Okay. So in the step response, I don't know if I can. Yeah, this looks good. So you can see that we have overshoot here. Then from here it goes down and it settles in this 2% or 5% band, whatever. MATLAB takes into account the 2% band. Okay. So this gives you the step response. So this is a very simple code to get the step response for any transfer function. Okay. I hope this makes sense. Please remember the command step and TF. That was it for from here. Now we'll move to the next question. Okay. For this open loop transfer function, which is given by GSHS is equal to this, sketch the root locus and determine the range of K for this which the system is stable. So I'll just give you a very brief recap of root locus in case you have forgotten. It's very easy. So first step is identify poles and zeros, right? Your poles are S is equal to 0, -2 and -5. Zeros, we don't have any zero, so it's none. Okay. Then what we do? We determine the asymptotes. What are the number of asymptotes? It's n minus m, which is 3 minus 0, which is 3. Then what is the angle of asymptote? It's given by 2k plus 1 into 180 degrees upon 3, where K is 0, 1 and 2. Your angles are 60 degree, 180 degree and 300 degree, right? Just put the values 0, 1 and 2. You'll get the answer. Then we look for breakaway points to know if there are routes that are coming in and they would break in to go to some other part, or if there are two branches coming from two poles and they would break in to go to zeros, or break away to go to poles. So any of these things can happen. So, okay. How are breakaway points found out? You solve dk upon ds is equal to 0. Then you get the intersection on real. So we can write for real axis segments. Okay. Then stability range. When is the system stable? When the system is stable when all closed loopholes have negative real parts. That means the with the increase in gain from 0 to infinity, it should not happen that the root locus is going in some other part, like the poles are traversing in the right half of the S-plane. If that is the case, then for all those values of k, the system is going to behave in unstable manner. In case you're not clear about any of the topics that I am discussing today, please refer to the videos that are already shared with you on YouTube. All of them have all the concepts with questions discussed in detail. Typically, stability corresponds to K. All of these are important points that is why I'm writing it down in the left half plane. Okay. So this is all for this question. Now we'll see how we are going to implement this. Okay. So this is a very simple way in which we have written the transfer function to be equal to 1 upon s into s plus 2 into s plus 5. Root locus can directly be plotted r locus g. Okay. Title root locus of GSHS of the same transfer function. Let me run this. So this is your root locus. So just this r locus command was sufficient to give you root locus. From here you can solve many questions and identify if the things are correct or not. You see there is a pole at this point at 5. It goes to minus infinity. There are two poles here at 0 and what is the other value? Minus 2. 0 and minus 2, both of them come here. They break in. One branch goes here, one branch goes to this side. So it gives you how the closed loop poles are traversing by seeing the open loop behavior of the system. Okay. So, okay. This was simple, I believe. We'll move to the next question. Sorry. Yeah. Okay. Find the time domain specifications, rise time, settling time, and overshoot for this system. So a GS is already given to you here. Compare it with second order system, GS can be given omega n square upon s square 2 zeta omega ns plus omega n square. From here you can find out omega n square to be equal to 50, omega n to be equal to root 50, 7.071 radian per second. Okay. You can also write 2 zeta omega n to be equal to 10 from this. 10 is here. So your zeta is equal to 10 upon 2 into 7.071. You'll get this to be equal to 0.707. All right. So from here we'll try to find out everything. Let's first find what is the overshoot. It is given by e to the power minus zeta upon 1 minus 0 square mp into 100. It would be minus zeta into 0.70, yeah, pi zeta, sorry. 707 under root 1 minus 707 square. Right? Once you try to find it, I'm giving you the answer directly. You get it to be equal to 16.3%. Then let's move to settling time. Assume it to be 2% criterion. So TS is given by 4 upon zeta omega n. 4 upon 0.707 into 7.071, which is equal to nearly 0.8 seconds. So this is for you. Please revise the formulas. These are really important. Your rise time, okay, rise time, you know that it is given by pi minus cos inverse of zeta upon omega d. So you can really substitute the value of omega d from omega n under root 1 minus zeta square and put all of them here. And from here you'll get rise time to be nearly equal to 471 seconds. Okay. Let's check the MATLAB implementation for the same, because we have calculated a lot. Now let's see how MATLAB does this. Okay. So for now, yeah. So your numerator is 50. 110, 50 is the denominator. Transfer function numerator denominator gives you the closed loop transfer function. This step info of G gives you what are the performance specifications corresponding to the step response. Then we print rise time in 3 float format, matlab 3 places after decimal, settling time, and we print the overshoot. So info.overshoot, info.settling time, info.rise time helps us in accessing all of these. Then we plot all of them with grid. Let's run this. Okay. You can see rise time to be equal to 0.304 seconds, somewhat different from our calculation. Settling time to be equal to 0.843, we calculated it to be 0.8. And overshoot is a bit different. We'll have to see if we have missed something in our calculation. But this is how you find out. Okay. And this is the step response for the same system. Whatever we have done. All right. Okay. I hope this also makes sense. We'll move to the next question. Okay. So we read a lot about PID controller. The question is, We want to implement a PID controller in MATLAB. For this system, GS is equal to 10 upon S square plus 2S plus 10 to minimize the steady state error for a step input. So we want to plot the step response for the system and we want to tune the PID controller. So what all you can do? So we have written the transfer function here. This PID tune is the function that can be called. Now you can have PID here, PI here, PD here, all options are available. We wanted to have PID. So it is PID tune G PID. Then this PID controller is tuned according to our system to have the to achieve some like good level of operation, good level of performance. So you get KP, KI and KD values to be this for our system. Okay, so this was really easy. And when you have this PID controller, you can analyze the step response. So I'll run this. So this is the step response with PID controller and your steady state error. So since you've used the controller, you would expect that since you have some good value of KI, your steady state error should be low. So you can see that steady state error is really low. So the PID tune function tunes the PID controller to get low steady state error, fast transients, etc. Okay, so this is one of the functions that you can always use. Okay, now we'll move to the next question. Okay, given the transfer function GS is equal to 50 upon S into S plus 10, plot the Bode plot using MATLAB. From the plot, determine the gain margin and phase margin. Verify the stability of the system based on these margins. Okay. First of all, there are some very basic things that I'll tell you that you should remember. What is gain margin? It's a factor by which can be increased before it reaches instability, right? What margin you have before you are going to reach the verge of instability? Your phase margin indicates how much phase can decrease before instability occurs. Okay, so how do we make sense out of them? A few interpretations. If gain margin is positive, the system can tolerate an increase in gain please remember these points. If PM is positive, the system is stable. If either of gain or phase margins, if either margin is negative or close to the 0, the system is on the verge of instability or already unstable. Okay. Now, after you know all of this, we'll see this question. So we want to plot the Bode plot, and we want to see what are the gain margins and phase margins, etc. So this is your code in which we have defined numerator and denominator. We have written transfer function, found out the closed loop transfer function, or the transfer function only. Then in figure, we will plot the Bode plot. We've written margin G. This plots the Bode plot, as well as it is going to calculate gain margin and phase margin for you. Okay, you get the you get the margins from here: GM, PM, WCG, WCP. Gain margin, phase margin, gain crossover frequency, phase crossover frequency. All of them are made available in this margins. Then we want to display gain margin is what, phase margin is what, at what crossover frequency, both of them. Okay, let's see. So this is your Bode plot for the same. So anytime you're drawing the Bode plot on your own, you can definitely check from MATLAB if you're in the right place or not, if you're drawing it correctly or not. This helps you verify as well. And then the gain margin is infinity, and the gain crossover frequency is infinity radian per second. Phase margin is 60.5 degrees, 53 degrees at 4.55 radian per second. So this is your phase crossover frequency. Okay, I hope this is clear. So it was very easy. You just had to write margin here. If you did not need margin, you just wanted the Bode plot, you could have used Bode. Bode of G. That gives you a Bode plot. It does not give you the frequency domain specifications. It gives you the plot basically. Okay. Now, okay. For the open loop transfer function, GS is equal to this. Use MATLAB to generate the Nyquist plot. Determine whether the system is stable using the Nyquist criterion, and indicate if there are any encirclements of the critical point, -1, 0. Okay. So what we'll do? What what do we actually know about Nyquist plot? Some common points. Show how the frequency response encircles the critical point -1, 0. What does Nyquist stability criterion states? It states that the number of encirclements around -1, 0 in counterclockwise direction should equal the number of poles in the right half S plane for the system to be stable, right? Okay. And what interpretations do we make? Counterclockwise. Or I would not write this. The only point important is if there are no encirclements or CW encirclements, clockwise encirclements, equals the number of right half plane poles, the system is stable. So we've already seen all of these when we were doing Nyquist stability criteria. Okay. Okay. So our question was we wanted to plot the Nyquist plot and check if the systems are, if there are encirclements and the system is stable or not stable. So how we can see that? So you can see here the transfer function is defined here. You need not write in this way. Okay. It is written in like three different 1 0 matlab s to the power 1 ka 1, s to the power 0 ka 0, and the second term and the third term. Basically in this format it is written. You can always simplify it and write it in a single array form. Then the G is the transfer function. Your Nyquist plot is plotted using this function, calling this function Nyquist of G. Just this gives you the Nyquist plot. I'll run this section. So this is your Nyquist plot. And you can see that there are no encirclements happening over here. But you can always see that how the things are going on. So this is one of the ways. I basically want to tell you what are the functions that we are using and how they are being called to get the answers. Okay. We'll move to the last question for today. So let's say you are told to find the stability of the system using Rauthov's stability criteria. How would you do? So this is a sample code for the same. You are supposed to create a function and then that function helps you in constructing the routes array, and then you can write if else statement to see or to determine the stability of the system, like if there is say change in sign, how many sign changes are there, if the entire row is 0, what is the case. So all of these can be written in the form of if else statement. I'll give you a brief introduction about this code. So let's say as our question said, these are the coefficients. Route array, route of coefficients constructs a route array as over here. This array is somewhat problematic now. I'll show you. So what we'll actually do, just don't go on this route array because it is giving some wrong element over here, -5. I think it should be 2 into 3 minus 4. 6 minus 4, 2 upon 2 it should be. So it should be 1. But here there is some issue, that is why it is creating some problem. So we'll see what are those problems. You can identify them on your own. But we'll see what is actually happening in the code. Okay. So we just want to determine what is the first column. Are there any sign changes? If there are sign changes, then the system has those many right of plane poles and is unstable. If the system does not have any sign change, then it is definitely going to be stable. Now, this function route array is important. So we want to remove any leading zeros that we have in the characteristic equation. Then we want to find out what is the number of coefficients. Then we want to arrange it in the form of route array by dividing it by 2, that it should go in alternate fashion. Then we want to construct the route array by positioning it. Okay, then we want to hand one of the cases could be that so this is basically the matrix thing that we do, uh, not matrix thing, but the multiplication which we make and we divide by the same number. So this is going in this loop for the entire time till we have the elements left in the routes array. Then sorry, then there is a special case in which we have entire row of zeros. Then we find the auxiliary equation in that case, create auxiliary equation, differentiate the auxiliary equation, replace the zero with the derivative coefficients. So this is basically how you can have a function. And in MATLAB, it is compulsory that all the functions should be placed at the end of the code. You cannot have them in between, you cannot have them in the beginning. So this function is present at the end of the code, and here this is the part where you can really see that the functions are being called, and you are able to generate routes array and determine the stability of the system. Please have a look at this code, make necessary changes, and this will help you as a like template for creating any other functions that you ever wish to create. Most of the controls uh, control functions or the functions are already available that help us in doing the important calculations or important representations or important algorithms that help us to determine the stability of the system. They are already available in the MATLAB. They already have the functions. So you can always refer to them. But yeah, when they are not available, you are definitely supposed to write a function and call the function to get the desired output. So apart from this, I want to just yeah. So this is the Ogata book that I was talking about before also in this lecture. This is a very important book. It will help you in preparing for your exam. It will help you in strengthening your concepts. It will also help you in writing the MATLAB codes. Please refer to this book. This is the best book available for control engineering. Now, so one of the MATLAB problems that I did not take was this one, that in case you have some numerator and denominator defined for a transfer function and you want to convert it into state space representation, where you want to have uh, the number where you want to have different ODE, first order ODEs corresponding to some big order differential equation. Let's say you have second order differential equation already available with you. You can convert it into two first order differential equations. So the state space representations really help you in doing them. So ABCD is the input matrix, output matrix, and all sort of things. They can be converted using by calling this function TF to SS. That means transfer function to state space representation of numerator and denominator. So you immediately get the values of A, B, C, and D without doing any calculation, without finding the number of state variables, writing it in matrix form and everything. The MATLAB gives you if you call the function TF to SS. Similarly, there is another function which helps you convert ABCD to a transfer function. It is SS to TS. Okay, that helps you. So this book is really good for practicing all the question answers. Please go go through this book. I'll also upload it in the this folder in which we are supposed to update our PPTs. I'll be uploading them there. I'll be uploading the MATLAB codes as well. But all of you must go through this, and you can also practice all the MATLAB questions that are given here. So this book contains all the type of questions that I have already showed you, be it an assignment, be it in, as a part of MATLAB problems. All of them are there. These block diagram reduction is also there. This helps you in practicing that how the blocks are going to be placed. Please go through them. And yeah, all of these are similar problems. Then you can go, so you can see this complete book will help you. So you have a chapter for transient and steady state response. Then you have a chapter for mathematical modeling of different systems. You have a chapter for root locus method independently. Compensator is also here. You have border plot, Nyquist stability criteria, PID controllers, modified PID controllers. Yeah, these are controllability, observability. They are definitely not in your syllabus in classical control systems. But in case you're interested, you can always go through them. Then there are some other methods, control systems design methods, which include pole placement and observer design and all of those things. So yeah, if you're interested, this book is a must. So I think you can always go through, look upon this book to get much information. Please solve the questions that are available here. It will help you a lot. And if you're interested in MATLAB, because control systems with MATLAB is much helpful. So please try to implement in MATLAB. You are already familiar with basics of MATLAB, that there is an editor, there is a command window, there is a workspace. Workspace contains all the intermediate variables. All of them are stored in some format over there. The command window is the one that helps you in some real-time calculations, and moreover it displays the outputs of your script. And there is an editor. There is also a live editor that I showed you today. So try to use them. In case you do not have MATLAB license with you, in case your institute does not offer you MATLAB license, you can do one thing. There is something called MATLAB Online. Go to MATLAB Online, register there and use it. It's free for 1 month. You'll be able to learn a lot of things. You can also use Simulink. So in MATLAB, you have another thing called Simulink. In case you know, uh, I'm not able to Simulink. Should be in home. Yeah, this is Simulink. When you click on it, you'll see a window coming over here. So let's say I create a blank model. Learning MATLAB will be very helpful every time. This is getting a bit slow. So there are many tutorials already available. So you can always refer to them. It's taking some time. I'll show you on the internet itself. You can search MATLAB Simulink. See, you can design, simulate, and deploy. So this is the basically this kind of screen that you'll get. So it is a wind turbine model. So it is able to do this. Then, so you do all sort of things. You can design your electric vehicle over there. You can design a simple power grid system over there. Autonomous vehicle over there. So this kind of thing where you have some inputs, some outputs going. You already have various motors available or over there. You can read the current, you can read the voltage, you can always correct an ammeter, a voltmeter, a scope. Everything is there. Okay, so these are some projects that are, see this electrification project. It has, okay, it has a DC source, then it has a current sensor, then it has a MOSFET. So many MOSFETs are connected. It has RL connected over here, and it has a PID controller connected over here. A driver is designed over here which takes some inputs PWM and gives sorry, it takes some duty cycle and gives out the phase and PWM output. Everything, there is some reference voltage given over here, there is some V out coming over here. So subtraction of this goes into controller. So this is what we saw in the control course, right? There is some output, there is some reference, subtraction goes into the PID controller, and it is used to drive the circuit. So this is, in this case, this is a driver and it is controlling the turning on and off of MOSFET. So this is happening. So Simulink helps you a lot. There are many lectures already available. You can start from anywhere uh, for Simulink. So this is the window that you'll get when you open a blank window. And from here you can click on this library browser. In library browser, you have these many things already available with you. You have many control, you have robotic system toolbox, everything related to power system, everything you have UAV system, vehicle dynamics and everything. Even for communication side also, you have everything. You have all the logic operators, maths operations, matrix operators. Just click on anyone. For example, let's say uh, I click on vehicle dynamics. Then I get this, see, power train, sensors, steering, suspension, and all sort of things. I double click, I get options. What steering do I want? Let's say I click on kinematic steering. Double click. It asks me for something, rack and pinion and everything. I've clicked OK. It is getting slow. So it's taking some time to come. But this is what you have understood, right? I hope it is clear. All of these are making sense. Yeah. So this is the way in which you can insert the block. You have some angle coming in, you're having some outputs going angle left, angle right and everything. So all of these things you can use. So MATLAB would be really beneficial if you have taken the course on control system. If you have understood control systems, this is a very good tool for you and a good starting point. So I think you can always start and go with this. Okay. So with this, we end the course or the interaction sessions on control system. It was nice to have interacted with you all, taught all of you, and hopefully the questions and solutions that we discussed are helpful to you. Hope you have a good grasp of the course. If you have any problems, please see the old videos again. The questions were from all the arenas of control systems, and they would help you in clarifying all the concepts. So yeah, with this we end today's lecture, and all the recordings and slides will be made available to you. So thank you.
Madam,
Yeah.
madam,
Yeah.
hello, madam, gate calculator or